Assalamualaikum and good day to all who watching this video. My name is Rizman and I will explain about introduction and basic principle of the system. Aiman, he will explain about schematic drawing and explanation. Amirul Hafiz will explain about method of performance analysis. Ahmad Zulhilmi will explain about method calculation of the system, and Aina Syafiqah will explain about suggestion of the system improvement. I will start the presentation with introduction and basic principle. The purpose of this paper, which is on the fact that some fraction of the fuel's chemical energy is not fully released inside the engine during the actual combustion process because of incomplete combustion. The percentage amount of the released energy from the injected fuel or the utilization ratio introduce the concept of the combustion efficiency. As shown as this figure, it is assumed that the mass of fuel supply to the engine per cycle is fixed. A fraction of the fuel's chemical energy, which is Q, can be transferred into the working fluid, and the remaining part of the fuel energy cannot be utilized and it is considered the waste. This paper studies an Otto cycle model with its irreversibility originating exclusively from the expansion and compression process. You must be thinking, what is Otto cycle, right? Let me explain. Refer the PV diagram. 6 process occurs. First is process 0 to 1. A mass of air is drawn into piston or cylinder arrangement at constant pressure. Process 1 to 2 is an adiabatic or isentropic compression of the charge as the piston moves from bottom dead center BDC to top dead center TDC. Process 2 to 3 is constant volume heat transfer to working gas from external sources while the piston is at top dead center. This process is intended to represent the ignition of the fuel-air mixture and the subsequent rapid burning. Process 3 to 4 is an adiabatic or isentropic expansion. Process 4 to 1 completes the cycle by a constant pressure, constant value process in which heat is rejected from the air while the piston is bottom dead center. Process 1 to 0, the mass of air is released to the atmosphere in a constant pressure process.
Hello and Assalamualaikum. My name is Muhamad Aiman and I will explain about schematic diagram of Otto cycle. So in Otto cycle, we have four process, which is isentropic compression, volume constant heat addition, isentropic expansion, and volume constant heat rejection. Initially, the piston is at its lowest position, BDC, which is bottom dead center, and the cylinder is full of air. The piston moves from BDC to TDC, which is state 2, top dead center. The compression of air occurs isentropically, ending at point 2, and thus rising the pressure and temperature of the air. This process is taken as adiabatic because the time taken during the compression is small due to high speed of engine. And then for the state 2, 3, which is constant volume heat addition, the piston is temporarily at rest at TDC position, and heat is added instantaneously in the air of cylinder from the tank for a short period so that both pressure and the temperature rise to highest at a constant volume. And then the next is state 3-4, which is isentropic compression. The air at a high pressure and temperature expand isentropically, causing the piston to move from TDC state 3 to BDC state 4. This is also, we call it as power stroke because the work is done by the system. Like the compression before, this process is also adiabatic as the time taken during expansion is quite small due to high speed of engine. And lastly is state 4-1, which is constant volume heat rejection. The piston is momentarily at rest at BDC state 4, and heat is reject to the heat is reject from air of cylinder to external reservoir or external tank for a short period so that both pressure and temperature decrease at a constant volume to its initial point, which is state 1. Note here, there are no exhaust and intake process in the Otto cycle as the engine operate is closed cycle so that the working fluid is restored to its initial state at the end of each cycle and the mass of air in the cycle remain fixed throughout the whole process. Thank you.
Assalamualaikum. My name is Mohamad Hafiz, Ismail. I will talk about the method of performance analysis of this case of study. For this case of study, we study about the performance or performance analysis for irreversible auto cycle. So, the analysis of the such studies are categorized into groups, which is classical thermodynamic approach and finite time thermodynamic approach. For classical thermodynamic approach, we analyze duration of state variable with energy of system, and finite time thermodynamic approach is extension of traditional thermodynamic to deal with processes which have explicit time or rate dependency. So for next, we for the analysis of a irreversible auto cycle, first we have the combustion efficiency approach to lead to a qualitative understanding of how engine loss can be reduced. Second, application of classical equilibrium thermodynamic on the modeling of thermal engines. So we apply this classical equilibrium thermodynamic into the model of this case of study, and to find the data or whatever. Third, focus on the heat transfer in the compression and expansion process and assumed to be irreversible one. So for the final, classical thermodynamic provide the limiting case of a simple process. So when the case is limiting, we are easier us to get the result and data and analysis for this case of study. So next is the auto cycle model. This is four basic process in this auto cycle. So in this case of study, we are going to focus on isentropic compression and isentropic expansion. This is because the auto cycle model contains irreversibility originating exclusively from expansion and compression process. So that's all for the method performance analysis for this case of study. Thank you.
Hi, Assalamualaikum. My name is Ahmad Zulhilmi, and I will cover for the calculation method of the system. So for the calculation of the system, there are two methods used, which is the first one is first law of the thermodynamic. The first law states that the change of the internal energy is equal to the difference of the heat transfer into the system and the work done by the system. As you can see in the equation, E2 minus E1 is equal to W minus Q. E stands for internal energy, W stands for work done, and Q refers to the heat transfer. And the second method is use the second law of the thermodynamic. So the second law of the thermodynamics states that the difference of the entropy is equal to the different heat transfer over temperature. If the S final is equal to S initial, it can consider as the reversible process. And if the S final is greater than S is initial, the process considered as the irreversible. As you can see, this is the TS diagram we get from the paper. The TS diagram is very helpful to get the formula involved the calculation of the system. Based on the TS diagram, the formula for the work output can be derived by using the basic formula, which is the isentropic compression efficiency, isentropic expansion efficiency, combustion efficiency, heat addition for the Q in of the system. The MA here is the mass of the air. So the net formula involved is the fuel chemical energy factor, which is the alpha, and then the next formula is the fuel energy supplied, and the last one is the heat rejection. So QLHV It is the Q of the lower heating value, and MF is the mass of the fuel. That's all from me. Thank you.
Soon I'm going to give you a few suggestions on how to improve a system, and in our case it is an Otto cycle. There are two ways based on my findings. The first one is to use a lean fuel in our system. Lean fuel basically means we need additional air in the fuel. The ratio is like 14.7 to 1 parts of fuel, and it also can increase the engine efficiency. And the second one is to increase the compression ratio, but this one is also have limit. Okay, the first one, it can cause a very high pressure sudden explosion frequently in our structural limits of the engine. In a simple analogy, it's like we give the hard blow by using the sledgehammer to our piston and the system in it. Okay, based on the graph here, it shows that this one is the cycle pressure versus volumetric compression rate. When we give a high volumetric compression rate, the cycle pressure will also becoming high. So that's why it has a limitation.